So we've looked at the calorimetry problems and we've looked at specific heats, but let's go ahead and put it all together and solve a problem um, using calorimetry. All right, so remember that we're using constant pressure calorimetry. This is the coffee cup calorimetry, and so the applicable equation is shown here, where the heat that was used to increase the temperature can be calculated by finding the mass of the solution, multiplying it by the specific heat for the solution, and then multiplying all of that by the change in temperature for the solution. Because if you think about it, whatever the reaction is that's happening on the inside of the water, that's what's heating up the water itself or the solution itself. And so the heat given off by the reaction is given to the solution itself. So let's go ahead and look at what a question or a problem might look like for this type of concept. So if a student mixes 50 milliliters of a 1.0 molar hydrochloric acid and 50 milliliters of a 1.0 molar sodium hydroxide in a coffee cup calorimeter, the temperature of the resulting solution increases from 21 degrees Celsius to 27.5 degrees Celsius. Calculate the enthalpy change for the reaction in kilojoules per mole. Notice the units, that's important, of hydrochloric acid. Assuming that the calorimeter loses only negligible quantity of heat, that the total volume is 100 milliliters and that the density is 1.0 grams per milliliter and that the specific heat is 4.18 joules per gram Kelvin. Notice we've got a lot of assumptions down here, but all of these assumptions are valid assumptions for this type of question. Um, they will not change the results or vary the results very far from what they actually are to what they should be with these negligibly effective assumptions. That is, they'll have negligible effects. All right, so the first thing we want to do is go ahead and calculate the mass of the solution. Well, if we take the volume of the solution and multiply so that we're canceling the milliliters and going to grams, we'll end up with 100 grams of solution. Next step, the temperature change, that is delta T. So delta T is the final temperature shown here minus the initial temperature shown there. Final minus initial equals 6.5 degrees Celsius or 6.5 degrees Kelvin. Now remember that the difference between, or the conversion between Kelvin and Celsius, if whatever the temperature is in Kelvin, you add 273, and that makes it whatever the temperature is in Celsius, you subtract 273 and you go to Kelvin. Or if you're in Kelvin, you add 273 and it'll take you to Celsius. So that conversion is actually fairly simple. And then the last thing we have to do is remember that if we're talking about the heat needed to warm up the solution, that heat is being given off by the reaction. And so the heat of the reaction will have the opposite sign of the heat of the solution, because the reaction is where the heat is coming from. And if we're concerned about the heat of the reaction, we're going to have to change the sign. And so our final equation will look like this, where the heat for the reaction is the negative of the heat capacity times the mass times the temperature change. So we got the heat capacity for water. We're assuming that the solution is the same as the heat capacity for water, and that the mass is 100 grams and that the temperature is 6.5 Kelvin. So now we multiply all of these together and we see that we end up with negative 2.7 times 10 to the 3 joules. Well, if we want to convert that and get rid of the exponential notation, we can just convert it from joules into kilojoules, and it ends up being 2.7 kilojoules. Now notice there is one thing that's a bit of an error in here. we said that it's 100 grams. If you look at this really closely, there's only one significant figure here. But remember, we're making the assumption about the mass of the solution, so we didn't bring in significant figures for particular uh, that particular variable. Okay, so this is fantastic. We now know how much heat was given off to increase the temperature of that solution by that 6.5 degrees Celsius or Kelvin. So what we have to do now is find out how much hydrochloric acid was used during the course of the reaction. So if you take the volume of hydrochloric acid, convert it into liters, and take this concentration, because it's in molarity, remember molarity has units of moles per liter, multiply these two together, we'll find out how many moles of hydrochloric acid we ended up using. So if we go down here, this is the volume in liters. This is the concentration. We ended up using 0.050 moles of hydrochloric acid. Now to find the heat that was given off on a kilojoule per mole basis, we take the kilojoules that was released total from the reaction, divide it by the number of moles of hydrochloric acid that was reacted, and we get this value. We see that it ends up being 54 kilojoules per mole of hydrochloric acid that was neutralized.